Alright, thanks for watching. And today we would like to solve something really cool called the half-heat equation. Or other people usually call it the heat equation on the half line. And you'll see the method of solving it is pretty neat. So consider the following equation. ut equals to k uxx, and with an initial condition, ux0 equals phi of x. But this time, unlike the regular heat equation, which is on the whole line, this time we'll do the half-heat equation, for which we assume we just have it on the half line. Namely, for x positive. So it looks something like that. The line starting at 0 and going to infinity. And unlike before, where we had the whole line and no boundary conditions, all of a sudden we do have a boundary condition. Because this line on the left side, it has a boundary or a wall. And what we'll do, we'll define a new boundary condition, u of, I think, 0t equals 0. Namely, we will require u at this point for all time to be 0. So u of 0t equals 0, and we would like to know what is uxt. Namely, given any position at any time, what is the value here? And the cool thing is, this has a very nice physical interpretation, because remember what the heat equation does? It measures the temperature of a metal rod. So here what we have, it still measures the temperature of this half rod, except what does this boundary condition mean? It means that we're putting an ice cube on the left-hand side. In other words, we're insulating the left endpoint to require that the temperature at all time is 0. And the question is, what will happen to the temperature at all x and t? Okay, as I said, pretty interesting equation, pretty powerful, but as I said, what's awesome about this is the method of proof, because we will do it by laziness. Because we know how to solve the problem on the half line, on the whole line. So the question is, how can we adapt the question on the half line to become a question on the full line? So as they said, like overcome, adapt, and something else. And for this, we use, interestingly, the idea of an even or an odd extension. And why? Because ideally, again, we have this function, on positive x, and we would like to kind of extend it to a function for all x, while at the same time having this boundary condition still valid. And so again, really it boils down to the following. Suppose f is defined. So let f of x be defined on for positive x on 0, infinity. So this thing. And again, the question is, how can we extend f such that the value of 0 is still 0? Well, and this is what's called an oddification. So, definition, the oddification I like to call this FOD. X is defined as the following. Let me put it here. Again, it's a function on the whole real line defined as follows. FOD of x is, if x is positive, so from 0 to infinity, where's my eraser? So from 0 to infinity, FOD is just f. So because it's an odd extension, so it has to agree with f on the interval. So it's f of x if x is positive. So it looks like this. Moreover, at 0, remember odd functions at 0, they have to be 0. So we define phod of 0 to be 0. So it's 0 if x equals 0. And lastly, how do you do it for negative x? Well, you want it to be odd. And remember, odd means, f of minus x is minus f of x. So literally, you take this function and reflect it about the origin. This might look something like that. Okay, not defined here. Not defined here, and this is phod. So it's minus f of minus x if x is positive, negative. And what does this satisfy? Well, first of all, you can check. It is indeed an odd function, kind of by definition. And moreover, it equals to f when x is positive. And this is precisely what we'll need. Namely, a function which is odd, but that agrees with the original function if x is positive. Good. Now, how can we use this to solve the half-heat equation? Well, as I said, let's extend the problem on the whole line. So now define, if you want to solve the following equation. Now solve ut equals to kuxx on the whole line. So from minus infinity x to infinity. And what we want to say, well, we want to say initially we want u of x0 to be phi of x. But that doesn't quite make sense because phi, the initial condition, is just defined for positive x. So this is phi. So the question is, how can we extend this phi on the whole real line? Well, just use phod. Luke, I am your father. So this is phod. And again, why do we do this? Because we want a problem on the whole real line. So we solve the following problem, ux0 equals to phod of x. It's a good thought. And there will be a reason why we use the odd extension. Because notice, technically the problem on the whole real line doesn't have a boundary condition. But then the question is, how will we still get u of 0t to be 0? We'll see. So, then we have this. Let's solve this problem. So then, I guess this, well, let me just check something. Yep. Then, we know how to solve this problem because it's the whole heat equation on the whole real line. So we know the solution is just given by uxt equals to the initial condition convolved with the fundamental solution. Sxt convolved in this time with phod of x. And I like to remind you what the fundamental solution is. It's just a Gaussian kernel if you want. It's 1 over square root of 4 pi kt e to the minus x squared over, I believe, 4 kt. Again, the fundamental solution of the heat equation. And what is convolution? It's just the integral from minus infinity to infinity of s of x minus y t phod of y dy. And again, as I said, by definition, or I guess by the formula for the solution of the heat equation, this solves this problem. But then the question is, does this also solve our original problem? And yeah, you betcha. So here's why. So claim this u above, right, u of xt equals s convolved with phi, solves our original problem. So it solves ut equals kuxx, and then u of 0t equals 0, and u of x0 equals phi of x. Again, that's for x positive. And it's almost by wishful thinking, because look, this solution solves the PD on the whole real line. So it probably should also solve the same PDE on the half line, because it's just the same equation but on a smaller interval. So if this is true for all xt, where x is anything, this is also true for all t and x positive, because it's just more specific. Now, what about this? U of 0t. Well, let's plug this in. Well, u of 0t, by definition, is integral from minus infinity to infinity. S of 0 minus yt, phi of what? dy. And that's integral from minus infinity to infinity of s of minus yt, phi of what? dy. Now, let's look at s. Notice s here, it's even in x, so s of minus y, well, it's also even. So the point is, this is an even function. And by construction, phi is an odd function. So you're integrating, even times odd is odd. So what you're doing, you're integrating an odd function from, if you want, minus infinity to infinity, and therefore the integral of an odd function over a symmetric interval becomes 0. And again, we're assuming everything is integrable and everything. So the awesome thing is, in fact, we didn't even need this formula. Even though we don't know what u is on the finite interval, or the half interval, sorry, just knowing that phi is odd, we know that u of 0t is 0. And again, that's the beautiful thing about oddification. You don't know what your function is. You don't know what your solution is, but because we require things to be odd, we know the value at 0 is 0. Last but not least, why is ux0 equals phi of x? Well, we know u of x0 is phi of x by our original PDE, but this is valid for every x. Now, if x is positive, we know something more. We know that phi equals to phi for x positive, so indeed, u of x0 equals phi of x. So, again, without barely needing the formula for the solution, we already know that u solves our original PDE. Okay. Now, by the way, I'm not claiming this is the only solution, right? I mean, there's some other way, that you might be able to prove this, but I'm just saying this is a solution of the half-line problem. The last thing we still need to do, well, this is a bit awkward, or should I say fuckward, okay? Phi, right? What do I want to say? Yeah, the problem is this just involves phi. Ideally, we would like to have just phi. So all we need to do, last but not least, is to deconstruct this to actually get a formula just involving phi. So let's do this. And which makes sense because we started out with phi. We should probably end up with phi as well. And so let's just deconstruct this. So this is the integral from minus infinity to infinity, s of x minus yt, phi of y dy. Now, remember what FOD is, right? FOD, it's basically think of it as phi for x positive and minus phi of minus x for x negative. The value at 0 here doesn't really matter because we're integrating. And so let's just split it up. It's the integral from minus infinity to 0 of s of x minus yt, phi of what? dy, plus the integral from 0 to infinity of s of x minus yt, phi of y dy. But here's a nice thing. For y positive, or at least non-negative, we know that phi is just phi. So we can just replace this by phi of y. And from minus infinity to 0, phi is minus phi of minus x. So this becomes minus phi of minus y. Okay, let's keep this as it is. This one, let's just do a quick change of variables. So no, I don't want to use u because it's our solution. Let's use p. So let p be minus y. Then dp, it's minus dy, which we precisely have here. Right? This is minus dy. And then p of minus infinity, that's infinity, minus infinity, p of 0 equals 0. So we end up with the integral from infinity to 0 of s of x plus p, t, phi of p, dp, plus the integral from 0 to infinity of s of x minus yt, phi of y dy. And look, it almost looks like the same integral, right? Except this is from infinity to 0. The other one is from 0 to infinity. But the nice thing is we can make this into an actual integral minus integral from 0 to infinity of s of x plus something, t, phi of something, d something. Before I wrote p, now let's just go back to y. You see p is a dummy variable, so it doesn't matter now what you name it. Or if you're really confused about this, let y be p, and then use a u sub. So this becomes integral of s of x plus yt, so minus of that, phi of y dy, plus integral from 0 to infinity of s of x minus yt, phi of y dy. Lo and behold, at the end, you get your solution. So you basically get u of xt. It's integral from 0 to infinity of s of x minus yt minus s of x plus yt and phi of y dy. Ta-da! And again, what is S? Well, if you really want the explicit formula, it's 1 over square root of 4 pi kt integral from 0 to infinity of e of minus x minus y squared over 4 kt plus e to the, minus e to the minus x plus y squared over 4 kt. And then phi of y dy. Ta-da! So again, proof by laziness. We didn't want to work hard at all. We had the equation on the half line. We just extended on the whole line by using oddification because it forces the function to be 0 at 0. And then we just unwrap the formula in some sense. And by the way, I will give an example next time because it's pretty cool. But suppose you want to solve the Neumann problem, ut equals to k uxx. But this time you force the derivative of your function to be 0. And then u of x0 equals phi of x suppose you want to solve this problem. The good news is it's almost symmetric. Instead of oddification, use evenification. And then turns out the only change in the formula is here you put a plus instead of a minus. So it's a nice exercise for you to try, but that is it, at least for today. All right, I hope you like this, and if you want to see more math, please make sure to subscribe to my channel. Thank you very much.